Hello, my name is Tanisha, and this video deals with D, JK, and T flip-flops. This is the second video in a series of 5 dealing with designing synchronous counters. If you haven't already watched the introductory video or do not have previous knowledge of flip-flops, I suggest you do so, as in this video I assume you have a basic understanding of the SR flip-flop, the concept of the clock, and what a sequential circuit is. This video seeks to briefly outline the D, JK, and T flip-flops, explain the concept of a characteristics table, give the characteristics table for the D, JK, and T flip-flops, explain the concept of an excitation table, and develop the excitation tables for the D, JK, and T flip-flops. The first flip-flop we will be considering is the D flip-flop. The D flip-flop is also known as the data or delay flip-flop. The SR flip-flop has an indeterminate or unstable state when S equal 1 and R equal 1. The D flip-flop seeks to overcome this shortcoming by having D feed into the S input and its complement feed into the R input. This ensures that S and R are always complementary to each other. On this slide, we see the logic diagram of the D flip-flop. Here we see D being fed into the S input, and here we see D complement or D prime being fed into the R input. This is the clock input. These are seen in all of the logic diagrams that follow, as the inputs are only passed to the NAND gates during the clock pulse. We can view the output Q as the value of the bit of memory. The D input serves to write the values of 1 and 0 respectively into memory. Thus, this circuit can function as a 1-bit memory, as the output is the most recent value applied to the input. Here we see the truth table for the D flip-flop. When the present state, or QT, is 0 and D is equal to 0, the next state, or QT plus 1, is equal to 0. When the present state is 0 and D is equal to 1, the next state is 1. When the present state is 1 and D is 0, the next state is 0. When the present state is 1 and D is 1, the next state is 1. From this, we can see that the D flip-flop performs a set operation and a reset operation. A set operation occurs when the next state is set to 1, regardless to the value of the present state. A reset operation occurs when the next state is set to 0, regardless to the value of the present state. Next, we consider the JK flip-flop. Flip-flops can perform 3 operations: reset, set, and toggle. As the D flip-flop only involves 1 bit, it only performs the set and reset operations. The JK flip-flop involves the use of 2 bits, allowing for all 3 flip-flop operations to be performed. Here we have the logic diagram of the JK flip-flop. Note that the J input can be compared to the S input of the XR flip-flop, as when it alone is high, the output is set to 1. The K input can be compared to the R input of the SR flip-flop, as when it alone is high, the output is set to 0. The JK flip-flop allows for both inputs to be high, unlike the SR flip-flop. When both inputs are high, the toggle operation is performed. Here we see the truth table. When j is equal to 0 and k is equal to 0, the next state is equal to the present state. When j is equal to 0 and k is equal to 1, the next state is equal to 0. When j is equal to 1 and k is equal to 0, the next state is equal to 1. When j is equal to 1 and k is equal to 1, the next state is equal to the complement of the present state. The operation that occurs in the first row is called the hold operation, as the present state is held in the flip-flop's memory and produced as the value for the next state. The second row showcases the reset operation. The third row showcases the set operation. The operation seen in the final row is the toggle. This function holds the present state in the flip-flop memory and produces the complement of the present state as the value for the next state. Look at the T flip-flop. This flip-flop is known as the toggle flip-flop. It is referred to as such as when it is active, the toggle operation is performed. The T input is fed into the J and K inputs, which are tied. Here we see the truth table. When the present state is 0 and T is 0, the next state is set to 0. When the present state is 0 and T is 1, the next state is set to 1. When the present state is 1 and T is 0, the next state is set to 1. When the present state is 1 and T is 1, the next state is set to 0. When T is equal to 1, the toggle operation is performed. When T is equal to 0, the hold operation is performed. Now that we have looked at the various flip-flops which will be used in this series to design counters, let's take a look at some of the tools you will be using to actually go from a sequence of numbers to the implementation of a counter. The first one we will look at are the characteristic tables. The formal definition of a characteristics table is that it is used to define the logical properties of a flip-flop by describing its operation in a tabular form. All this is saying is that the characteristics table is used to define the operations that can be performed by the flip-flop and showcasing these operations in a table. As we saw from the truth table, the D flip-flop performs two operations, set and reset. The characteristics table just showcases that in a more succinct manner for the D flip-flop. As we saw from the truth table, the JK flip-flop performs four operations: hold, reset, set, and toggle. From this characteristics table, we see that the set and reset operations are independent of the present state QT. As we saw from the truth table, the T flip-flop performs two operations, hold and toggle. The next tool we will examine in our proverbial toolbox for designing counters is the excitation table. This is the final section in this video, after which one of my colleagues will be giving you an introduction into counters and insight into the actual design process of a synchronous counter. An excitation table is one that lists the required inputs for a desired change of state. This is a very useful tool in the design of synchronous counters or finite state devices in general. as we generally know the present and next states of the device and have to determine how to get from the present state to the next state. The D flip-flop does not require excitation tables as the required input is the desired next state. The X's in this excitation table for the JK flip-flop denote don't care conditions. For don't care conditions, the input value does not matter. That is, it can be a 1 or a 0. In the next slide, we develop this table. To go from a present state of 0 to a next state of 0, two operations can be performed: hold and reset. Hold is performed when J and K are both equal to 0. Reset is performed when J is equal to 0 and K is equal to 1. These two are combined to give J is equal to 0 and K is equal to X or don't care. To go from a present state of 0 to a next state of 1, the two operations that can be performed are the set and the toggle. Set is performed when J is equal to 1 and K is equal to 0. Toggle is performed when J is equal to 1 and K is equal to 1. These two operations are combined to give J is equal to 1 and K is equal to X or don't care. To go from a present state of 1 to a next state of 0, the two operations that can be performed are the reset and the toggle. These two JK input combinations are added together to give J is equal to X or don't care and K is equal to 1. To go from a present state of 1 to a next state of 1, the two operations that can be performed are hold and set. These two JK input combinations are added together to give J is equal to X and K is equal to 0. This is the excitation table for the T flip-flop. To go from a present state of 0 to a next state of 0, T must be 0. To go from a present state of 0 to a next state of 1, T must be 1. To go from a present state of 1 to a next state of 0, T must be 1. To go from a present state of 1 to a next state of 1, T must be 0. The T flip-flop performs two operations, hold and toggle. For the first and fourth row, the present state is held as the value for the next state. Hence, T has to be set to the value which allows for data to be stored in memory, which is 0. For the second and third row, the present state is complemented to give the value for the next state. Hence, T has to be set to the value which allows for data to be toggled, which is 1. In closing, this video should have helped you in understanding the D, JK, and T flip-flops a bit more, as these are the fundamentals which are used as the basis for the design of synchronous counters. This is the focus of this video series. In this video, we also began to place the tools we needed to design synchronous counters into our toolbox. These tools were the characteristics tables and the excitation tables for the three flip-flops that were discussed in this video. The next few videos will give you the rest of the tools you need, the general process that you will follow for designing synchronous counters, and the application of this process to the design of certain counters using the three flip-flops we have discussed in this video. Thanks for watching!